Okay, hello everyone. Well, I want to talk about my all-time favorite science discovery and some problems that arise from it, Rule 30. So last week I announced prizes, $30,000 worth of prizes for answering seemingly straightforward questions about a creature that I first encountered nearly 40 years ago now, Rule 30. So I should probably start off by explaining what Rule 30 is. It's an example of a cellular automaton, and we can see how it works by doing this. We can just say, show the rules for the cellular automaton. And these rules say we have a line of black and white cells, and at every step, we color a particular cell based on the color of the cell above it and to its left and right. Okay, so that's the rule. So now what we do is we say, take that cellular automaton, let's start it off with just a single one, and let's run it for, let's say, 20 steps, and let's show the result. Okay, here it is. So let's see how this worked. All right, so let's take that cell there. So that cell there is underneath a black, white, white configuration. Black, white, white gives black, and so that's black. Let's look down here. That cell there that's white, above it is a black, 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 gives white. Okay, so that's Rule 30. You know, one thing I realized I forgot to mention in the in my explanation of Rule 30 here is what it is in terms of Boolean algebra. So we can say, if we think about these as bits, trues and falses, we can say Boolean function, and this is a 3-argument Boolean function. I think that goes like this. We say kth Boolean function in 3 variables. Okay, so there it is. So that's Boolean function. If we say make the truth table for that, well, actually, if we can just say make the rule plot for that, we'll see it's the exact same function. Now, what we could do if we want to is we say for this, so we can make that as a function of p, q, and r, and we can say Boolean minimize, and we might just do that by default. So there it is as ands and ors. So the minimal version of it, I can show you. It is an OR and an XOR. Let's see whether we can actually get it to do that here. We would say something like, let's see what happens if we say XOR here. Oops. Dear. So this is what happens if I start exploring. I immediately start dealing with things that, so A and F is what I want. Okay, so that's P XOR Q XOR R XOR Q and R. So that's another form for Rule 30. But you can represent it in terms of, you can represent this rule in terms of a Boolean function, and you're just applying that function over and over again here. Okay, so what would we like to know about this? Well, let's look at the center column of cells here. So first of all, let's look at what happens if we run it a bit longer. Let's run it for 200 steps. And what we see happen is that even though it's a very simple rule, there it is, very simple initial condition, what we get out looks pretty complicated. And for example, over on the left, there's some regularity. Over on the right, if you look at the very, very edge, it's periodic. It's just black, 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 black. One step in, it's already alternating, and then it quickly gets to be increasingly long before it repeats. But the real center of the problem is the center column here, and we can just look at the sequence of values in that center column, and so we can compute that here. If I just say generate the center column, sequence of values in the center column, I just say there, I want 200 steps, and I just want the center column out. And I think this should do it. There we go. And so the question is, what can we say about that center column? And for example, let's generate, I don't know, let's generate 10,000 steps of the center column. And let's say C 10,000, let's say C 4 for 10 to the 4 is this. And then we could say, for example, let's just take accumulate 2 times C4 minus 1. That will kind of give us a random walk. And then let's say list line plot of that. That will kind of show us every time there's a 1, it'll go up. Every time there's a minus 1, it'll go down. So that's showing us kind of a sign of the randomness of that center column. Or for example, we could just say make counts of C4. Let's compare the counts of 1s and 0s. They seem roughly the same. Okay, so what I have been curious about for a very long time is what can we actually prove about the center column of cells? And so far, we know basically nothing. Empirically, we know lots of stuff. Empirically, we know the center column of cells looks completely random with respect to all kinds of statistical and other tests of randomness. But we don't know anything really. So the 3 problems that I have identified that I'm offering $10,000 each for solutions to these is the first one is, does the center column always remain non-periodic, or does it eventually repeat? Does each color occur equally often? So 1 and 0 occur equally often. And the third, slightly more difficult to explain problem is, if you want to compute the nth cell here, can you do that more quickly than by just going ahead and computing every step in the evolution? Well, actually, I'm asking something even tighter than that. I'm asking, can you kind of just jump ahead and figure out what the nth cell will be without using at least about n operations to do it? You know, if you just compute this pattern here, you'll actually use n squared or n squared over 2 operations, because to get the nth row, not only do you have to go junk, 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 junk down n times, but by the nth row, the width of it is 2n plus 1, actually. And so that means that the number of operations, the number of times you have to apply this rule, goes up like n squared. But this problem here is asking, does computing the nth cell, can it be done in less than order n steps? So, okay, those are the problems. And, the statement is very simple, yet really, in nearly 40 years, we haven't made any progress in answering any of these questions. As a practical matter, we've used the results. So, for example, for a long time, the randomness of the center column of Rule 30 was used as the random number generator in Wolfram language. So actually, if you go look up random integer, one of the methods for random integer, method to seed random, okay. One of the methods here is the Rule 30 CA. And that, in fact, the way that's done, because we don't want to, we're basically sampling the center column, but we're not sampling the center column of an infinite width pattern, which is what this is. We're sampling the column of a finite width pattern. And when you have a finite width pattern, I mean, if I were to do this with, let's imagine I just say, let's just imagine that I make this a center array with a single 1, and I want, let's say, 40, width 40, then that's what it looks like. And eventually, oops, I wanted to say width 40 there. Eventually, let's do this with like width 10. Eventually, as you can see there, it repeats. And in general, if you have width n, it has to repeat after at most 2 to the n steps, 2 to the n minus 1 steps. In practice, Rule 30 repeats after about 2 to the power 0.61 steps. But that's still enough that for reasonably large n, we can use it as a good generator of random numbers. So you might ask of these problems, well, what evidence do we have about them? Well, for example, we've computed 1 billion bits. That's actually not. You can actually use the built-in cellular automaton function in Wolfram language is pretty efficient, and it can readily crank out 1 million bits quite quickly, because we were kind of rushing to get 1 billion bits in time for the announcement of this prize. We actually broke down and used custom GPU code to get to the 1 billion bits, and it took a couple of days only at that point to do it. But with 1 billion bits, we can start asking, what can we say about what happens with 1 billion bits? And I should first of all say that the 1 billion bits are available in our data repository. It's just resource data of this 1 billion bits thing, so we can go ahead. It's probably going to be really slow. Let me do it with 1 million bits just to show you kind of what happens. So let's say I pick up my million bits here. So here's my million bits, and then I just go over here and I say, let's call it, to be consistent, let's call it C6, the 10 to the 6th list of these things. Okay, so this is now going to load in. Oh, it was already loaded here. Okay, so let's check the length. Well, let's do a counts here. So we can say counts of C6, and that will tell us the relative number of zeros and ones. So it's really close to being an equal number of zeros and ones. But our problem is, can we prove that in the limit of an infinite number of cells that it's exactly 50-50, 0 and 1? Okay, and we can do all kinds of other things. We could test, is it periodic? Is that million bit thing periodic? Actually, let's say find transient repeat C6, and actually I don't want to print out the results here. Let's say we want to make it see whether it can find the so this is going to be searching for a repeat, and it's going to say how long is the transient, how long is the repeat. Okay, so it didn't succeed in finding. Actually, that's interesting. Let's take a look at the very end of this. Let's take a look at the first 10 bits. Aha. So it did find what it thought was happening in this 10 to the 6th bit sequence was that it had this number, 999,993 things that didn't repeat. And then at the very end, it said it had 4 things that repeated. So it's a little bit tricky. So let's ask it to look for, let's say, some more repeats. Let's say I'm only going to count it as a repeat if it repeats 10 times. Okay, so if we do that, and then we say, how long is the transient, how long is the repeat? It's going to say the transient is of length 1 million. In other words, it never found a repeat, and the repeat is of length 0. And we could do all kinds of things. Like we could, for example, we could say, let's try this. Let's split that thing into sequences of zeros and ones, and then let's ask it to, so that's going to make it into, that's going to, if I do this, let's do it for the C4 case. So that's going to split it into sequences of ones, followed by sequences of zeros, followed by sequences of ones, and so on. And so we could ask questions like, what's the longest sequence that we get in there? So if we split, well, in this case, we could just say, let's see, we could say, well, we could just say the length of those, and we could say, for example, let's say the count of the lengths of those. Okay, so that's saying that there's a 1 length 13 sequence of identical elements and a bunch of much shorter sequences of identical elements. And in fact, if we say, let's sort those. So that's saying most often we have a sequence of length 1, then about half that often we have a sequence of length 2, and so on. Okay, so we can try all sorts of tests of randomness. Well, all the ones I've tried, it's passed. Actually, I think we have a nice collection of new tests for randomness. If we look in our new function repository, we have a bunch of tests for randomness that have been provided there. Let's see if we can look for that. Assuming that the search is working well. Okay, there we go. So we've got things like spectral randomness test, run count randomness test, all kinds of run length randomness test, all sorts of randomness tests, which actually should be run on. So I mean, if we say, okay, so this is a sequence. So what we want to do is to run a chi-square test here. So this is now saying chi-square randomness test. Let's run it on C4. And it's going to have to load in the function. And it's going to tell us, okay, the p-value. So that's telling us the probability. Let's see what the interpretation is here. Okay, is and returns a p-value for whether it is random. Tests a sequence for equidistribution and returns the p-value. So, or for example, we could try here, we could say, let's do another one of these tests. Let's do one that might be interesting, an arcsine law randomness test. Okay, so same thing, we can just run this and ask for how it does there. Oh, wow. I don't actually know how to read that. I mean, what we could do here, okay, so those are some examples of what happens when we run randomness tests here. Let's ask for some analogies to this problem. So one obvious analogy, we're asking, how random is this sequence of bits? We could ask, how random are the digits of pi? So let's say we generate digits of pi to 1,000 digits of pi. Okay, there they are. We could generate them if we wanted to. We could generate these digits in binary. So we could say real digits of pi in base 2, let's say the first 1,000 digits in binary. So there they are. And that's then a sequence that we can sort of compare to the sequence we're dealing with here. And the thing about the digits of pi is there have now been about 30 trillion of them generated. And although there haven't been incredibly elaborate randomness tests done on the very large number of digits of pi, there have been tests of randomness done on up to billions of digits of pi, and so far nothing has ever seemed to be non-random in the digits of pi. So one question you can ask is, well, can the digits of pi ever repeat? That's one thing we can absolutely answer, because the only numbers that have digits that repeat are rational numbers. So if I say, for example, what's 1 over 181, and I look at that to 300 digits, you'll see this is kind of a cute one because it goes 0, 1, 2, 3, 4, 5, 7, 9, 0, 1, 2, 3, 4, 5, 7, 9, but it eventually repeats. And every rational number has a digit sequence which repeats in any base. But can you say any more about it? Like, for example, could you say for pi that in base 2, it has an equal number of zeros and ones? Absolutely not. Nobody's been able to say anything like that. Can you say pretty much any other sort of statistical fact about the digits of pi? Nobody knows anything. And so one question you can ask is, are there sort of things like naturally occurring numbers about which you can say anything? Well, there's kind of one class of examples. There's a thing called the Champernowne number, which is a number that, let's look at what that is. If we look at it, if we just look at, let's say, 200 digits of the Champernowne number. Oops, oh, I'm wrong here. I need to say what base I want to do this in. So let's say base 10. Okay, so that number goes 0.1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, etc., etc., etc. So let's take a look at the digits of the base 2 Champernowne number, so it'll just be zeros and ones. Let's look at, okay, so we want the base 2 Champernowne number. Let's see, what do we want to do here? We want to say digits in base 2, let's say 100 digits in base 2. Okay, so what we'll see is 1, 1, 0, 1, 1, 1, 0, 0, 1, 0, 1. So it's the numbers in base 2 counting up. Okay, so if we now ask for, let's see, we just want to get the first of this, so it's the mantissa of the thing. We now can ask, for example, for counts of this. And okay, well, that was because we didn't. Let's try going to 128. Ah, interesting. Very interesting. So we know that eventually the fraction of ones and zeros will converge. So actually, let's look at something. I'm now curious. We can either compute this from the Champernowne number, or we could just say generate integer digits of n base 2, and let's make a table of integer digits base 10 going up to n goes to, let's say, 2 to the, let's just say 2 to the 8. And then I want to flatten this out, and that will give us a bunch of digits here. And now I could say, I could do that same counts thing. So this is now claimed to be something. Wow, that's pretty weird, actually. This should be a number that has the property that every digit occurs with equal frequency eventually. So let's take a look at how that works. So what we're going to do, let's just look at the successive ratios. Actually, we could go ahead and look here at that same thing we computed before. 2 times that thing minus 1 accumulated, and do a list line plot. Oh, very cute. Okay, so it's a weird scalloped thing, but it turns out it should be the case that the number of ones and zeros should, on average, be equal. So this means that eventually, let's take a look at what this does. So let's go out to 10 to the 10. Humpty hump, what am I doing wrong? Well, it better be the case that, oh, maybe am I doing something wrong here? This is an example of a so-called normal number, which has the property that every block of ones and zeros should occur with equal frequency. But I think the issue here is that it's prejudiced towards ones, because the leading digit of each of these is always a 1. So if I say rest here, I think we'll get a very different result. Yeah, there we get a result which keeps on. So that's something where we're cutting off the leading 1 there. I have to admit I'm a little confused by this. Now I'm embarrassed that I'm very confused by what's happened here. Let me just show you. So for Rule 30, some things we know about Rule 30. Okay, so if we go to my big book, needless to say, on page 30, is a picture of Rule 30. That's page 29. There's a bigger picture on page 30. Isn't that cute? Okay, so if we look at the notes here in the book, it has some facts about Rule 30. By the way, that's the form of Rule 30, bit XOR of the left bit, or the middle bit and the right bit. And I have to embarrassingly say that I need to mention that I should put that in my blog post, and I think I forgot to say that. It's kind of a nice fact about Rule 30. That's the simple form that it has. Okay, so really, in the case of do all the cells occur equally often, sort of no naturally occurring, for example, digit sequence is known to have that property. There are sequences one can generate that have that property, but they don't sort of occur in sort of an integrated way. This particular pattern from the Champernowne number is a nice self-similar pattern. Okay, but it's very different from the Rule 30 pattern. In the case of Rule 30, that's what we get. It's looks much more like a random walk. And from what we can tell, it really is basically a random walk. And if we look, for example, at the sequence of how frequently zeros and ones occur at different lengths, what we will see is that let's see, we'll see there that what we get is that's a table that shows how frequently zeros and ones occur up to 1 billion bits. That's the number of ones that occur, that's the number of zeros that occur. So the ratio is incredibly close to 1. But can we prove that it's exactly 1? So I don't know what kind of mathematics might be able to do this. There are some facts that we know about Rule 30. We know some facts about sort of the local behavior inside Rule 30. We know facts about the left-hand edge of Rule 30. But all the facts we know about the left-hand edge of Rule 30 are facts that have to do with for example, we know that that on the left edge, it is very close to periodic. So we can see that if we take a Rule 30, let's say we just take one of these things here. Let's do this. And let's take a look at the left and right edges. Okay, so let's look at this. And then let's say, how do I think about this? I want to trim out the zeros on the left. How would I do that? I would say, one thing I could do is I could say, rotate left by an amount that is, let's try this. I could say map indexed, rotate left. Let's live dangerously. I wonder if this is going to work. That should be at every successive step, making it go further. I think I wanted to say rotate right. Okay, so that's showing me the left-hand edge. That's showing me the pattern after I've kind of rotated it right. So that's showing me the left-hand edge, and it's showing me that on the left-hand edge, things become periodic, right? And it's showing, in fact, that there's a line of separation between the periodicity on the left and the randomness in the middle. And that line goes at a speed of about 0.25 steps per time step. And actually, I have to show you a little bit of Rule 30 history. It's kind of fun. When I first started studying Rule 30, I asked everybody I knew if they could figure out what was going on with Rule 30. And let's see if I can just pull this up here. One person who had interesting things to say was a physicist named Dick Feynman. That's a picture of me with him, but this is, oops, that's not what I wanted. I wanted to go down to those. This is, these are some notes that Dick Feynman made trying to compute the rate. This was back in 1984, trying to compute the rate of the wiggling of that line between sort of order and chaos. I mean, if we look up at one of these pictures here, let me make a bigger picture of this. If we make, for example, let's make a picture with, let's make one with 1,000 cells across. Okay, so here, if I make it a bit bigger, you can probably see there maybe just about, you can see this kind of line between sort of order on the left and chaos on the right. And that line has kind of a random walk, but it's not an unbiased random walk that equally goes left or right. It's a biased random walk that goes about 0.25 cells per time step to the left. And there's a little argument that one can give that that Dick Feynman worked out. If you assume certain kinds of randomness on the part of this pattern, then you can predict using what's called mean field theory in physics, in statistical physics, that the random walk should be biased by exactly 1/4 of a cell per step. And so I think this is, but it turns out it's not exactly that. And this was a sort of attempt to compute what it really was. And I think, yeah, Dick Feynman was a good calculator. I can't do any of these kinds of working it out by hand, but that's computing after several steps. That's computing the sort of probabilistic estimate of what you should get. And I think that's another one of these probabilistic estimates of how the Rule 30 random walk should go as a function of as it goes down the page. You know, I was thinking of making a little scrapbook of Rule 30 because I realized that and I know I need to put this I know I need to put this in the scrapbook. Okay, so that's a little bit, that's kind of some of what I wanted to say. I mean, there's Rule 30 has shown up in all kinds of funky places. Like, for example, one of the fun ones recently was this train station in Cambridge, England, that has metal plates that are in that arrangement. And turns out that arrangement, there's a zoom in of the photograph, that arrangement is exactly the right-hand side of Rule 30, this kind of diagonal image of it. It's kind of fun. So that's what that train station pattern. I haven't yet seen this thing in the flesh. Eventually I'll visit Cambridge, England, and I'll see the metal Rule 30. So you know, when it comes to these problems, it's really very unclear how to approach them. We can talk about some different approaches one might take. I think one of the things that's a conceptual question is, is there any way these questions might not have answers? Is there any way that there might just be no way to answer these questions? Well, it would be exotic, but it is conceivable. The main way that it could fail to be answerable is, well, these are questions about sort of infinite behavior. And whenever you have a question about infinite behavior, you have to use kind of theorem proving methods, or you have to prove theorems. You can't just say, well, let me qualify that. For example, for problem 1, if it turns out that after a quadrillion steps, Rule 30 suddenly becomes periodic, the center column suddenly becomes periodic, then you could just compute a quadrillion steps and know that that happened. So for example, the way that could work is, let's say this random walk here, suddenly things conspire in such a way that the random walk no longer goes off to the left, but starts walking chunk, chunk, chunk over the center. And eventually this repetitive behavior on the left-hand side takes over the whole pattern. I think it's extremely unlikely that would happen, but it's not impossible. We can't prove that that doesn't happen. So one thing we could do is just compute long enough that we can actually see it happening, and then we've got our answer. Now, but in most cases, there's no explicit computation that would answer one of these questions. So instead, we have to have a proof. We have to have something where we start from axioms, and we say, from these axioms, we can deduce, like Euclid deduced things in geometry, we can deduce what's true. And so one of the bad things that could happen is we think we know some reasonable axioms for mathematics. For example, the axioms of arithmetic, Peano arithmetic, or the axioms of set theory, things like this. But it could conceivably be the case that this is a mathematical question that just doesn't have a definitive answer based on the axioms that we normally use in mathematics. So that's a way that the answer to one of these questions could be, well, it depends what axioms for mathematics you use, what the answer is, which is a very weird possibility. But it means you just can't reach. We don't have a way to prove from axioms. It doesn't say that it's just saying we can't reach it using methods of mathematics. Okay, so questions. So someone is asking on the live stream, do I have a guess how much time will pass before any of the questions get an answer? You know, it's funny. Somebody who works with me just sent me email like 5 minutes before this live stream started, saying he thinks that maybe he's got a way to answer. Let's see, which problem is it? It's either number 1 or 2. I'm not convinced, but let me see. It's so you know, it is conceivable there might be a quick answer. I'll be very surprised. My guess is that the first question, does it ever become periodic, that's the easiest of these to answer. We know, for example, that no pair of columns can ever become periodic. No pair of adjacent columns can ever become periodic, and that's actually a fairly easy thing to prove. And that's kind of a, you know, so it's like we're homing in, and we can prove that not only can no pair of columns ever become periodic, a single column and sparse other cells to the left or right of it, that combined thing can never become periodic. So I think that this is kind of within sight. I mean, this problem 1 could be cracked in a month if we're lucky. You know, for pi, proving the irrationality of pi, I don't remember how many centuries that took. It was a little harder, but it's a different kind of problem. It's sort of qualitative the same, but not in detail the same. But so I think that one might be reasonably easy. These other 2 are pretty hard. Now, you know, in the subject of hard problems, about in 2007, I put out a prize about a Turing machine. So I had discovered that I'd enumerated possible Turing machines, and I'd found that the simplest Turing machine that behaves in a not obviously simple way is this particular 2-state, 3-color Turing machine. And I had a conjecture based on this principle of computational equivalence that I think is a really important, very general principle. I had a conjecture that this Turing machine will be a universal Turing machine. And that conjecture, so I put up this prize. And in that particular case, it only took 4 months to get an answer. It took a little bit longer to sort of nail down the answer. So this is let's see, we've got you know, this was the result in that case, and you can see this is not an entirely short thing, and it contains, you know, computerized proofs, and it contains a lot of detail and so on, and you can see the thumb there. So it's keeping on going and going, and it's a pretty long and elaborate proof. And that's I don't know what the length of the proof for some of these things might be expected to be. I mean, in the subject of things that take a long time to prove, people might have noticed in let's see, recently, let's pull it up here. Let's pull it up. Here we go. There was I tweeted about this in the NKS book. There's I list some Diophantine equations involving integers, and there are different kinds of equations. These equations involving cubics here, some of those equations were very simple to find, either to prove that there couldn't be a solution or to find a solution involving, let's say, 7-digit numbers. But I couldn't find a solution for that Diophantine equation, x cubed plus y cubed equals z cubed minus 3. And in that case, It turned out there was a solution found just a few weeks ago using this kind of network of about 1 million computers around the world, and that's the solution. It's this really these really long numbers. So that's another case where sort of there is a solution, but you're right at the edge of undecidability. You can find a solution, but it's a very complicated solution to find. So I don't know for these problems. I just don't know how hard they're going to be. And I would say this problem here, the third problem, does computing the nth cell require at least order n computational effort? That's one where we can start discussing, how would one even think about formulating that question? And for example, one thing we could say is, well, let's ask, is there any Turing machine that we can construct that will successfully compute the nth bit in the sequence without going through at least order n steps? But we could make it a little less than that. We could just say, let's run a Wolfram language program, and even with all the primitives that are available in Wolfram language, could we, given the actual implementation of Wolfram language, could we get something that runs in less than linear time? Okay, someone, Anteater of Power, is asking on our live stream, why Rule 30 over other rules? Well, it's my favorite. And the reason it's my favorite is if you look at all of the simplest rules, all the simplest cellular automaton rules. So this rule here, there are, you can see there are 8 bits here, and each bit can be either black or white in the result. So that means there are 2 to the 8 or 2 to 556 possible rules. And we can just go through and look at what do each of them do, just starting from a single black cell. And this is kind of a sort of classic experiment that I did a long time ago now. But we can redo it here. Super easy to do now. It was a little harder back in the day, although this has never been a particularly difficult program to write. But let's do it here. 255. There. Okay. So these are all the rules, and you'll see most of them. It's not difficult to answer the question, what do they do? I mean, some of them make nested patterns, but Rule 30 is the first of the rules where, just starting from a single black cell, the behavior is complicated and seemingly random. Another example is Rule 45. It's a little bit less easy to see what's going on because it keeps on making the background go from black to white. But if we look at Rule 45, we'll see the same phenomenon of the center column being apparently random. My guess is whatever methods work for Rule 30 will also work for Rule 45. We can keep going. Another one that's kind of cool and has complicated behavior is Rule 73. Here are things that are just essentially mirror reflections of Rule 30 and black-white inversions of these rules and things like this. I mean, like, for example, we can look at Rule 73, about which fairly little is known. I mean, I can show you Rule 73 here, and we could compute the same thing for Rule 73. So there are all the other ones. That there really nothing much more happens, except for Rule 110. It does some slightly different things, but it's not so interesting in terms of randomness. Okay, so there's Rule 73, 1,000 steps of Rule 73. And you can see it looks kind of complicated there. But if we look at, here, let me, maybe it's a little clearer if I show just 500 steps of Rule 73. And you can see, oops, let me make it so that it doesn't alias. I don't know what it's doing through the live stream, but let's do this. Let's do pixel constraint 3. Pixel constraint 2 better. Okay, so this is now showing 2 pixels per cell here without any anti-aliasing. And if we look at the center column here as a sample of what it's doing, what we see is actually the center column here is not so random. Let's look at what it is. Let's take the center column of Rule 73. Let's go down here and compute it. 500 steps. And let's get just the 0th, the center column here. Oops. That's not random at all. just goes periodically 0, 1, 0, 1, 0, 1. I'm kind of guessing that if we look a cell or two away from the center column, it might get a little bit more complicated. I don't know. Let's take a look at what does that one do. So we can get some indication of that by just doing one of our accumulation plots. And this is kind of the random walk plot. 2 times that minus 1. Okay, so that actually a bad example because I shouldn't have used. Let me try doing it. Well, what this is showing is that there certainly isn't. I don't know what I'm going to see if I just look at that sequence. I've got zeros and ones pretty far separated here. But let's take a look here. If I just do a counts on this, then okay, I've got 4 times as many zeros as ones. So if I assume that, then and I do my list line plot. So what I do is if I say if I just say I want to say minus a quarter and plus 1, that should kind of even out the zeros and the ones. Of that plus 1, that will give it, okay, and now I want to accumulate that. That will make it go down a quarter, so that should be about equal. Okay, there we go. Oh, wow. Wow, I didn't know that actually. So that's only one step away from the center column of Rule 173. I'm actually surprised by this. It's really looking quite random. Let's take a look at more steps. Let's take a look at 2,000 steps there. Oh, that was only 200 steps. No wonder it looked simpler. Wowee. So 2,000 steps, even just one cell away from the center column of Rule 73, we're already seeing good randomness, fairly good randomness. Now, I'm curious here, if I go 2 steps away and I look at the counts, wow, let's go 3 steps away. For some bizarre reason, at 3 steps away, it does the same thing. So actually, when in doubt, look at what my book has to say about one of these things. So I now have to look up in the index Rule 73. Okay, density oscillations, localized structures, properties of pattern from single cell, page 59. Okay, that's dandy. Now, Rule 73. Okay, let's see what I say here. Central region of the pattern goes 4 cells every 7 steps. Actually, I didn't know this. This is an interesting fact that from what I can see here, the I mean, I don't know for sure, but it looks as if, let's take a look at, I'm just now curious, if I go to 10,000 steps, it's going to take a little bit longer to work out. Okay, well, not so much longer. That's 10,000 steps of the column 1 to the right of Rule 30, in Rule 30. And we could go ahead and look. Let's look at that column, and let's look at the counts there and see whether, okay, well, that's pretty close to being ratio 1 to 4 of zeros to ones. So I really don't understand that, because I would have expected that if you have a periodic pattern in the center, that would sort of force the neighboring patterns to be similarly periodic. Let's just for fun, let's take a look at that question. So let's say we look at the center column here. We look at the things from let's say minus 4 to 4. So that's going to be just the center of this, and let's partition that in. Let's do 1,000 steps here. Let's partition that in size 50 things, and let's go ahead and make array plots of those. So this is now slicing it up And let's see what this does. Okay, so this is now the cells away from the center column of Rule 73. We can see it's left-right symmetric. And so that's looking at what happens. And so what this is saying is, for whatever reason, it's kind of interesting, it does this. Even though left and right are really random looking, the what you get at the center column, sort of the convergence of the two sides, is periodic. And actually, to kind of test out what's going on, we could just say the rule. Let's take a look at what happens if we look at the whole rule, the whole pattern, but we downsample it by a factor of 2 in each direction. Is this going to work? Can I just say downsample? Does this work? Let's see. If I just say 1,000 steps here, and I say downsample 2, 2, and then I say array plot that. Is that going to do the right thing? Or is that going to try and do some very clever piece of downsampling? Oh no, that did the right thing. Okay, so this is now, okay, so what we see there is it's really kind of random looking on either side, but there's kind of a black line in the center, and that is the periodic, left-right periodic thing. I'm actually now quite kind of inclined to try running this for, it's probably possible to prove that the center column has to be periodic in this case. Okay, we got some other questions on the live stream. So Vejero asks, I would guess random real probably uses sources of entropy like devu random or something. So that's right for seed random, but not for random real, because random real, if we seed random real in the same way, if we just give a seed here, we better have it be the case that random real produces the exact same sequence of numbers every time. So, I mean, if we say random real, 30 numbers or something here, that's going to give a definite sequence of numbers. And if we seed it again the same way, it better give the same sequence of numbers. And the seeding is done by using hardware sources of randomness. And that's important when we, like, for example, actually, I'm now curious. Let's do this. Just for fun, let's say make a parallel table. So let's find out how many processors I have on my computer. Let's say processor count, 12 processors. Okay. Not totally shabby, but not, could be more, but that's at least some number of, for my desktop computer, that's a decent number of processors. But if I say parallel table, and I say, if I say parallel table there, and I just say, I just was to say seed random, oops, that was the wrong thing. Actually, what I should do is to say seed random, open close, and then I say random real. And let's do that in a parallel table for, let's say, well, let's just do 12 because we know that's the count of the number of processors. So what we'll see here, actually, no, I'm going to do 24. Okay, so what we should see is it will start up 12 local kernels, and it will now run them. And it better be the case that, so each of those local kernels, oh yeah, every single time I do this on every processor, even though it's happening at the same time, it is seeding it differently. And so we're getting a different answer. Okay, and even if I were to do that on my single processor here, and I were to just say table of the seed random seed, then that's going to pick up hardware randomness and give us a different result each time. But normally you seed the thing. Now you're saying Rule 30 is not an efficient source of randomness. It's actually very efficient. It takes only a very small number of operations to compute the next random bit. And by the way, when you actually compute Rule 30 in a computer, you can do it with word-wise operations. You can do it by just doing essentially bit XOR of bit OR to compute the so that you're computing all the bits in the 64-bit or 128-bit word simultaneously. So Robbie is observing that the left-hand side of Rule 30 is definitely not random. Absolutely, the left-hand side of Rule 30, we could probably compute it, but here I had arranged it someplace up here. That's showing the that's showing how it becomes periodic, and the period increases. It stays period 2 for a long time, then it jumps to period 3, I think, and so on. In fact, we could go ahead and compute that if we want to. We could just say, let me think about this for a second. How would I do this? I would take this and I would say, instead of rotating right, I think if what I did here was to say take, yeah, I want to take the things that are all, comma, and then in this case, I want to take 100. I think this is right. That should give me, oops, if I didn't have this wrong. That should give me, if I flatten it out, that should give me the bits right by the center column, I think. And so if I were to take this, oh, no, I'm sorry, I think it's 200, right? Is that right? No, so what I've got to do is take this thing here, and I've got to sample it. I got to sample this thing in the middle here. And so that thing in the middle is, oh, actually, if I were to simply say part that, comma, 200, I think I would get the right thing. Oh, 100 then. I want to get, that will give me the center column there. Okay, why isn't that working? Oh, maybe I have to say 101 because I'm off by 1 there. Confused, I am confused. Let's see. This should be all, and then I want the column, do I want column 201 here? Yeah, so I'm messing up here somewhere. Maybe somebody can help me. What am I doing wrong? I'm looking at this, and I could say, well, let's just say rotate left. And here, I could say rotate left, hash, comma, 200 steps. So I think it's 200, if I'm not mistaken. Yeah, there we go. Okay, so that's the thing. Okay, so we're trying to compute the periodicity of these left-hand sides. So if we do the following, if we say this, so let's do it. Okay, so here, we can do that. And then if we transpose this, we will get those. And then for each one of those, we say find transient repeat. And let's insist that it repeats, let's say 10 times. Oh, and then let's say length / at that transient repeat thing. Okay. So this is showing us at the beginning there, those are the periods. So that's saying there's a transient of 23 steps. It's probably something up here, and then those second things there are the periods. So if I were to say, last slash at that, last slash at that, it will give me the successive periods of that left-hand side there. So you can see that it's approaching, it's getting bigger only rather slowly. Okay, so if I were to plot that, this is showing the progressive, period doubling effectively on the left-hand side of this pattern, and it's slow. All right, question is, about Plurmurant asks, what is the fastest way known right now to compute the nth bit in the Rule30 pattern? It's order n squared. The only way we know how to do it is to basically just run the solid automaton rule. Now, I'll show you a couple of things here. If there are some slightly more, there's some things that might seem slightly more efficient, but they're actually not. So for instance, if we look at the thing as a Boolean function, we can say, let's combine together the Boolean functions at successive steps. So at the first step, the Boolean function that we're using is given by a 3-term Boolean function as we have successive steps. So for instance, I was showing you at the very, very beginning here, as I mentioned, Rule30 is, let's go down here, I think I had it here. What we can do, let me think how to do this here, is, so that's the Boolean expression that we get in, I think this is in disjunctive normal form of ands of ors. So we can, if we say traditional form of this, it'll show it as ands of ors of nots. Well, it's actually ors of ands. So now we can ask the question, if we do 2 steps of Rule30, will we get a simpler to evaluate function, or will we get a function which basically takes both steps to evaluate it? And I guess what we could do, let's think how to do this. Well, we could just say one way to compute it is cellular automaton, and we want to do 2 steps. So we say nest of cellular automaton, comma, hash, comma 2, and then we apply that to all the 1, 0. Okay, so that's going to give us, that's going to give us the 2-step evolution of the cellular automaton. So if we did it for 1 step, if we did this for 1 step, what we would get is the tuples Actually, there's a better way to do this. I'm being silly. Yeah, I'm being silly. The best way to do this is to just apply the cellular automaton to let's if we did it for 1 step, and then we just showed the center cell, then this would give us that. What the heck? Oh, yeah. Yeah, I have to say, show us just the thing after 1 step. Okay. And I think I might be able to get it to automatically flatten if I do this. Yes, okay. So that should be, if I look at Rule30, that should be the rule plot. Actually, if I say, rule plot of Rule30, that should be, did I mess this up? That's not encouraging. What did I do wrong here? That's applying Rule30. starting. I am confused. Let's do this. Okay, so that is 1, 0, so that's the 0. What's that? What is that? What's going on here? Oh, I know what's happening. Oh, how confusing. I think this will work if I were to do this. No, I'm not sure what's happening here, because what I thought I was getting was the result. Okay, so if I do this, I get all those things. And then I think I thought I was just saying cellular automaton 30 applied to all of those is the evolution of each of these things. So, oh, that's right. 0, 0, 0, 1, 1, 1, 1, 0. Okay, what am I doing wrong here? I'm not sure what I'm doing wrong here. But anyway, if I were to do this and I were to say part of that, comma, all, comma, 2, I would get that cellular automaton rule. Now, if I want to go 2 steps, I just say 5 here, and I say 3 here. And unfortunately, I have to say nest that, comma, 2 applied to this. And that will give me the 2-step. So there's 2 to the 32. Here there's 2 to the 3 things. So if I convert that to from digits, comma, 2, that will give me the Boolean function that is, so that Boolean function of that number, comma, 5 will give me the 2-step Boolean function corresponding to Rule 30. So I can then say Boolean minimize of that 2-step Boolean function. And, well, actually, okay, fine. Let's just do it. So there it is. It's a little bit complicated. I could apply this to variables, let's say A1, A2, A3, A4, A5. But so this is what we get by, let's make it traditional form. So this is essentially the combined 2 steps of Rule 30 combined together. This is sort of attempting to sort of find the Boolean function given by not just 1 step at a time, but 2 steps at a time. And because I've done this before, I know that it actually doesn't really work. It doesn't get any simpler. If I go, let's really live dangerously and go 4 steps, and that would be 5, 7, 9 here. And so this is now going to give us, so that's a Boolean function. And if I say from digits there, that's going to be a Boolean function. So that's Boolean function of that, comma, 9. That's a 9-variable Boolean function. And if we say Boolean minimize, which might take, this might be completely crazy, I don't know. Oh, no, it isn't. Wow, I'm impressed. Our Boolean minimizer is fast. So that's showing us what you'd have to compute to go 4 steps at a time in this. Oh, actually, I made a mistake here. That's not 3, 4, 5. That should be 5 there. Sorry. Not clear it will make any difference, but let's try it again. Didn't make any difference. So that's the minimum Boolean function that you need to go sort of 4 steps at a time in this rule, and it doesn't help at all. Are the right and left-hand side of Rule 73 really identical? Yes, absolutely they are. And I can prove that to you very simply because I just make a plot of I just make a rule plot, and you can see that the the rule here is left-right symmetric. So because it starts off from a left-right symmetric initial condition, it's guaranteed to be left-right symmetric in the end. So right. Well, let's see. Any other questions or comments? I think we had some previous questions that came in that was sent in previously, which I could take a look at here. Is there a 3D version? Well, you can make 3D versions. You can certainly make 3D cellular automata. Sure, there are 3D cellular automata that have complicated behavior. I mean, this problem, if one's able to find a method for cracking Rule 30, it will probably be applicable to a bunch of other cellular automata. Yeah, so Mr. D was commenting that on the right-hand edge, the periods increase rapidly. We could do the exact same analysis that I did on the left-hand edge, on the right-hand edge, and yes, they increase rapidly, which means that that's kind of a suggestion that by the time you get in to the, here we have these comments, by the time you get all the way, I mean, these are all diagonals, and the diagonals are simpler to analyze than the verticals. But the diagonals do increase rapidly. I mean, I actually have a list of how much those increase. I think in here on the right-hand edge, yeah, the period seems to increase exponentially with depth. I actually didn't give, wow. Okay, so someone here gave that's nice. Someone here gave the successive periods on the right-hand edge of Rule 30. I don't think I seem to remember computing this at one point. But those are nice results. That's let's see, the statement being made, this person tracked it out to 2 to the 16, which happens not too far in. But that would be a nice thing to put in the, we've got a community section for people to post things about this. That would be a nice result. Let's take a look at what else is here. Okay. We're asking questions about what it means for something to be random. Well, yes, if you talk about algorithmic randomness, that is, what's the shortest program to compute the sequence, then Rule 30, the Rule 30 sequence is definitively not random because there is a very short program to compute it. It's just the program that runs Rule 30. That's a short to state program. Actually running the program may take a long time, but the program is short to state. So it's not algorithmically random. We don't know whether there are algorithmically random things that sort of our universe can generate. But sort of an important mystery about the universe is whether it is capable of generating algorithmic randomness, or whether somehow, if we only knew how to do it, we could sort of compute everything in the universe just like we compute something like digits of pi or the center column of Rule 30. So, okay, let's take a look here. We've got a pretty detailed thing here. Okay, so Craig on our comments has pointed out that certainly the whole of Rule 30 isn't a random raster. Absolutely. there are absolutely correlations between, if we generate a Rule 30 pattern, how many Rule 30 patterns am I going to generate tonight? Let's just generate one here. I'm going to get much faster at typing this particular thing. Let's just generate it with pixel constrained, so that just makes sure that it won't anti-alias on my, actually I need to pixel constrain it to 2, for example. Oh boy, already too big. Okay, so if we do this, then every local region, the vertical column can be random, but certainly a patch is not random. And the reason a patch isn't random is it's running this rule. So for example, if you had a bunch of black cells all lined up, then the next thing that will happen is that there'll be pure white cells. And then over time, the randomness from the outside will eat into this region of white. But it isn't the case that every the blocks here, there are very few possible blocks, because the only blocks that are possible are ones that follow this particular rule. So if we start off with some particular sequence, and so for example, we can figure that out empirically. Let's just take this, and for instance, let's say we make in that pattern, we partition it into, let's say, I don't know, 5 by 5, let's say 4 by 4 blocks, and let's do overlap 1, and then let me think what that's going to do. Hold on, let me just make a smaller version of this just so I'm not totally confused. That is making 4 by 4 blocks. What's the structure of that? That would be that thing. Okay, fine. So I have to flatten it once, and then I will get, okay, so if I take this and I flatten it once, I'll just get a bunch of 4 by 4 blocks. And so if I do that, and I say flatten this once, now if I do a count of that, then this will count the number of different 4 by 4 blocks. And what I'll find is that the number of 4 by 4 blocks is definitely not always the same. And if I simply ask, what's a good way to do this? Well, I could just do the values here, and I could just say histogram those values. That's not very convincing yet, but I think if I run this longer, well, actually, let me do the following. Let's say counts here, and let's just ask how many 4 by 4 blocks occur with non-zero frequency. Okay, so that's the length of the number of counts of the counts. So 320. But the actual number of 4 by 4 blocks that is possible is 2 to the 16. So of all 2 to the 16 possible 4 by 4 blocks, only 320 actually occur in this cellular automaton evolution, because once you have the rind of the 4 by 4 block, the thing at its top and its left and right, you've completely determined the innards of the 4 by 4 block. Okay, let's see. Question here. Is it possible to find some subsequence along the center column that does not exhibit the same kind of randomness as the whole center column? That's a perfectly good and interesting question, to which we know absolutely no answer. Yeah, I mean, clearly, so one question would be, could there be periodicity in the center column that is rare periodicity, like 1 in every 128 bits is always a 1? I don't know. Good question. It's a good question. We could test for that by doing, if we take, I think C4 was our list of the first 10,000 of these. I mean, this is pretty boring, but I could just take a Fourier transform of that and I could then take the abs of the Fourier transform, and then I could just say list line plot of the abs of the Fourier of that. That's pretty flat. So that means that in a good approximation, this is white noise. So what that means is if for example, every 15 cells was suddenly suddenly had was more probable to be black, for example, then this would show definite structure. So, for example, if we do this, I know if we take, for example, if we look at Rule 110, okay, so if we look at Rule 110, starting off from a random initial condition, so random integer, let's say 400 steps, let's say 500 down, and let's do an array plot here. This has the feature that its background has some definite periodicity. So if we did that same test here on this, we could just say, oh, I don't know, let's just take all of them. Let's just flatten the whole thing out just for the hell of it. And then let's do that same Fourier transform. So let's take this thing, let's flatten everything out. So we're just taking every successive column. And now let's say abs of Fourier of list line plot and oh, great. Okay, let's make this a bit smaller. Let's say 100 by, I don't know, let's just do 100 by 100. Okay, so what we're seeing here, look at all that structure. What we're seeing here is all kinds of structure that's reflecting, in particular, I think there's a period 14 behavior here, which we're seeing as, and I suspect if we do this, if we say plot range to all, okay, we're seeing a very big peak down there, and we're seeing these successive peaks here, which reflect the periodicity that we're seeing in that pattern there. Okay. Yeah, the Igblan is suggesting building a lookup table like one does in hash life, for example. That won't work here. The point is that in game of life, most possible configurations of cells do not occur, because most of the time, I mean, if we make a typical, let's say we just do an evolution here, we say game of life, and then we say random integer, let's say 1, and then let's make a, I don't know, 300 by 300 field of random things, and then let's evolve that for, let's say, 200 steps. Okay, so this is going to give us a big thing. Let's see what happens. Okay, so that's a big thing. And now I think if we do image 3D here, we might see something reasonable. Yeah, look at that. Isn't that cool? Okay, so let's make it bigger. And what we should see here, look at that. There's some, well, actually, let me go ahead and do this. Let's say do it for 500 steps. And then let me make that whole thing into an image 3D. And then, of course, it's going to take longer. Okay, so that's the game of life evolving in 3D. So we're showing it in space-time, right? And what you see down here, still not really, okay, what you see down there at the bottom, you see a bunch of gliders running around. That's what those streamer things are. But you see most of the time, it's evolved to some fixed things, and most of the field is just white. So most of the blocks, the n by n blocks of cells, do not occur. So that means the entropy of is low, and that means that it is a big win to say, well, don't bother to evolve that n by n block of cells. We can just know that an n by n block of zeros stays 0. The problem in Rule 30 is you'll never get a speed up from doing that, because every possible, not n by n block, but every possible block of length n in the pattern, when we have a pattern like this, in the horizontal thing, we can we don't know for sure, but it appears that every possible block occurs, and in fact with equal frequency. We know if we start the thing off from a random initial condition where every possible block occurs with equal frequency in the initial condition, then the same is true at every time step in the evolution of the system. Okay. So yeah, so the hash life trick won't work. Let's see. Is it an inherent property of two-dimensional cellular automata that they have low entropy like that? No, it's not. You can have perfectly well. You can when you generate. I mean, if I just were to generate a random sequence of, let's say I do this. I just say, let's say I generate. Let's say I say random integer. Oh well, I'd have to generate. You know what? The best thing to do is look at the documentation for cellular automaton, because it'll show me how to do this. And I say, let's say, multidimensional rules. Here's a typical cellular automaton after 30 steps. And what will happen is, if I just generate, let's say I just generate the first, I don't know, let me generate the first 50 of those. This is now a slice in, this is at a fixed time. And so you see all kinds of things happening. You don't see, you don't necessarily see anything that that coarsens out. These are just the spatial slices, well, the fixed time slices of those patterns. And no, they don't. Many of them are just like Rule 30. In fact, if I look at a space-time slice through these, they'll look a lot like Rule 30. So if instead of looking at the 30th step, what I do here is to look at, let's think how to do this. I want to look at the slice. Let's think how to do this. I'm going to look at 30 steps, but I'm going to look at the slice that is the slice that is at the center. I think it's this. Actually, if it's civilized, it will allow an wall there. Let's see whether this works. So let's say we take this and we make that rule 42 or something, just for good measure. Oh, wow. I think that should work. I'm surprised that doesn't work. If it doesn't work, it should work. Oh. Let's see what happens if I do this. The spatial offset. Oh, silly me. Okay, so I think it might be this followed by all. There we go. Brilliant. So what this is doing is it's taking a space-time slice through the pattern. Okay, so each of these now, these are slices at a fixed time. What I'm now doing is I'm slicing the sort of pyramid that you get in the space-time. Just, oh, come now. Wait a minute, let me look at what this does. I goofed somehow here. Oh, I see. I need to slice off, I think, one level of, what am I doing here? Oh no, maybe it's this. There we go, beautiful. Okay, so those are the sort of Rule 30 analogs, the space-time diagrams that you get from two-dimensional cellular automata. And it's not that remarkable. They're very similar to kind of Rule 30 case. If I were to show it, kind of this is just one slice. So if I were to show it, the depth sort of in and out, I would tend to see it sort of have, I don't know, we could represent with gray levels the stuff that is further deeper in or further out. It'll look very Rule 30 like. Yeah, okay. Well, let's see. Any other thoughts or questions here? Someone commenting that their formulation of algorithmic information theory might help with this. That would be cool if it's the case. I think. Well, as I say, that first problem about periodicity, I think, might be comparatively easy, though I'm not counting on it. But the other ones, I think, are pretty hard. And in a sense, the third one, to find out if there's a fast way to compute Rule 30, for the digits of pi, people believed that the only way to compute the nth digit was to compute all the previous digits and get the nth digit. But then this really cool, weird series that works in certain bases like hexadecimal was found, that allows you to kind of more or less just dip in at any point and find, let's say, the trillionth digit of pi. I say more or less because there's actually a little bit of probabilistic stuff going on there, that involves not allowing cascades of carries to kind of pile up too much. But in fact, that turns out, even though you can kind of dive in and compute the trillionth bit, it still takes you of order a trillion steps, because you still have to do arithmetic with length trillion numbers and so on. So you don't get to just sort of go and sample the bit without sort of paying your dues for a computation if it's the nth bit of order n. So that's how that works. It's yes, it's Simon Plouffe's amazing result. Simon Plouffe actually worked for our company for a while. There's a remarkable story of a person who memorized digits of pi and really was not schooled in fancy mathematics, but just noticed a lot of things, and ended up coming up with this really cool idea that everybody thought was impossible. It's a that's the kind of thing that might crack the problem 3 of the Rule 30 prizes, is some insight like that just comes really out of left field. I mean, we really know, we know, well, I will be amazed if it turns out that there's a faster than n way to compute the nth bit in the Rule 30 center column, because it would imply that that is a computationally reducible computation, and I strongly suspect it's not. I strongly suspect that, like many other kinds of computations, the only way to compute it is effectively just to run it and see what happens. But we know very few examples of things that sort of look random but are faster to compute than just evaluating each step and seeing what happens. I mean, clearly, if we have something like, let's say we have something like this, we can pretty easily go through and say here, oh, we can compute the value of any bit in this pattern much more efficiently than by going and just computing down to that level in the pattern. Essentially, what happens in this case, well, let me show you a simpler case. In this case, the value of the nth bit is essentially the bit XOR of the coordinate position of that bit. So if I were to compute the bit XOR of, so let's say it's I and X and Y, and I were to make a table of the bit XOR, actually what I want to do is I want to say table of bit XOR, let's see, if I want to say compute, let me try saying that equals 0, and then let me make the bool of that, which just turns it into 1 or 0. And then let me say make a table of that, X goes to 100, Y goes to 100. And then let me say make an array plot of that. Oops, I did the wrong thing here. Do I want to do this? Maybe I want to say humpty hump. Well, let's just compute. No, that's not what we want to do. Let's just compute the bit XOR value here. Oh, it looks like that. That's beautiful. But now oh gosh, how do we work this out? Oh, it must be the, oh, I know what it is. It's the digits of that. If we say integer digits of that, so we're counting the digits of that in base 2, and then we say bool of odd q of total of that, he says, which I could also do by computing, okay, that's the total, that's the odd q, that's the bool, which I could also do, oh, come now. I could also do that, which one is it? Growl, growl, growl. What did I get wrong? I've goofed this up somehow. But anyway, you can kind of see from this picture that there's some reason to think it would look like that. Okay, questions on the live stream. Do I suspect it's possible to get order n to the alpha with alpha less than 2? Yes, I do. I think it's possible to get it pretty close to order n. Because I think one should be able to use, well, I'm not certain, but I think it will be possible to get it less than order n squared, and that would already be an interesting result. But I'm predicting for just the center column, I'm predicting that you don't need to compute all the wings. Let's see. Yeah, I mean, if you could find, yeah, I'm saying if you could find, well, okay, if you can find an order n algorithm, no, it's not really. Look, the real test of computational reducibility would be like if I could only get this right. Let's think how to do this. This is, am I just getting the function wrong here? Let's just take a look. Am I just confused here? Is it the bit or of those? No, come on now. I know it's one of these. I'm going to be reduced to looking in my own book for this. Well, okay, when in doubt, look in the NKS book. And let me just take a look here. Methods for generating pattern from. Oh dear. Well, that's let's see, where is it? There's got to be one of these that gives the nth digit in the pattern. Oh, there it is. There it is. It's the bit and. Let's just take a look here. See, I knew if I did enough of these. Okay, now what it's saying is it's the bit and okay, if I say 1 minus sine of bit and, ta-da! Well, I got it slightly wrong here because that's got to be 128. That's got to be a power of 2. Let's say 128, and I've got it upside down. But there it is. There's the pattern. So what does this tell us? This means if I want to get the nth bit in this pattern here, then what I can do is I can just feed in the digits of x and y. Okay, so if I'm getting the nth row here, the specification of the nth row is the digital number corresponding to n, which has length log n, log to the base 2 of n, roughly. So in other words, what we're doing is we're computing here using log n steps. We're computing the output. And yeah, so yeah, that's a beyond Sierpinski. That actually, instead of Sierpinski has log to the base 2 of 3 fractal dimension, that has log to the base 2 of a golden ratio fractal dimension. It's rule 150, as you can see. All right, well, let's see. Are there any other questions or comments? And I'm really looking forward to seeing what people produce as an analysis of these problems. And I'm really hoping that we'll see a repeat of what happened with the Turing Machine Prize in 2007, and it'll only be a few months before somebody gets a result. I should emphasize what happens. I should emphasize that I'll be amazed if there is a really simple proof of any of these results. I mean, in other than, yeah, I'll be amazed. I think, yeah, Brian is asking, are there known cases of cellular automata generating true randomness? Depends what you mean by true randomness. Anything where the randomness is generated by rules, it's not, quotes, true in the sense of algorithmic randomness, in the sense that you can always figure out what the bits are going to be just by running the rule. I think John von Neumann had a quote that anybody who generates pseudorandom numbers, that is numbers that come from basically a computing a formula, is in what he said is in a state of sin, as in it's always going to eventually bite you. Actually, in the years since about 1984, when I first suggested Rule 30 as a random number generator, the Rule 30 random number generator is the only one that I know of that has survived all of those years without having had any non-randomness found in it. All other random generators have had all kinds of weird randomness. I mean, like for instance, if we take a good other source of randomness is let's say powers of something, let's say powers of 57 or something in base, let's pick a random thing in base, let's say base, well, let's just say base 7 or something. If we say that will generate for us a sequence, well, actually, let's say in base 73, and then we're going to generate these, the first, actually what I'm going to use is power mod because it's slightly more efficient here. I think that's the right thing. N goes up to 100. So that's generating those digits. I don't know whether those numbers are good, but anyway, let's take that and let's say, for example, let's take the last digit of that. So we want to say mod 2 of that. So that's going to give us a sequence of zeros and ones. Well, that's a cruddy sequence. I don't think that's very random at all. But let's say we take some number like this, and we say, so this is a very common way. This used to be a very common way of generating randomness, was to use a linear congruential random number generator like this. And so there are particular choices of numbers here that give a maximal length for their before they repeat. That's given, I think, by the Carmichael lambda function. Is that right? This gives the repeat time for those things. I've forgotten. Let's see whether we always a good trusty linear congruential generators. Oh, this is talking about sources of randomness people have used. Yeah, I actually have to. I have a copy of this book. It's always fun. The Rand Corporation published in 1955 a table of random digits. And the thing that's really fun about that table, I actually have a copy of it. I could go fetch it and put it on my document scanner here. What's actually particularly fun about that table is they published an erratum. And so, you might wonder how on earth was an erratum published to a table of random digits? The answer is they got that randomness from electronic randomness in, I think, triodes, vacuum tubes, and they discovered that they were pulling out digits a bit too fast, and so there were small correlations between the successive digits that they pulled out. So this supposedly random table wasn't really that random. Okay, let's see. Yeah, you should. Iggy is saying he'll look at what HashLife does. Yeah, absolutely, look at it. I don't think it'll do anything, but you should look at it. And then Vejero asks, why did I decide to post this challenge now? You know what? I've been trying to get around to it for a long time. I almost posted this right after the Turing machine thing was won, but I didn't get around to it. And I thought about doing it at some anniversary of a discovery of Rule 30, but I don't know exactly when I first saw Rule 30. I think it was June 1st, 1984, that I first generated a high-resolution picture of it. But I haven't really had a great excuse. I had a silly excuse. It was I'm getting totally ancient, so I turned 60, and I thought, gosh, I should do it. This is really corny for my 60th birthday because it's a 30 and a 60, and that's a factor of 2 and things like that. But that was my most recent really corny reason for posting this now. But I've been meaning to do this for years, and I've just finally got around to it. So, okay, well, wait a minute. Yeah, Iggy is pointing out the low order bits of these. I mean, there's a thing that's sort of an interesting analog, which is if you look at the digits of powers of 3 in base 2, then you get, let's see, if I just make a table of those, the first, let's say, 200 of these, and then I pad it on the left, and then I make an array plot. This is powers of 3 in base 2, okay? So actually, at least in base 6, that turns out to be exactly a cellular automaton. In base 2, it's not, because there are carries that are long-range carries. But if you look at this, the linear congruential random number generator would pick off the right-hand edge of this. And you can see in this case, the absolute right-hand edge is periodic. And as you go deeper in, it gets the period starts to increase quite rapidly. But that's what you'd get. That's kind of the visual version of a linear congruential generator. And by the way, in terms of the fast computation question, the one thing, this is one example where you get a cellular automaton-like pattern, but where there is sort of a skip ahead method, because if you want something to the power of 100, then one way to get a thing to the power of 100 is by repeated squaring. So you don't have to just go x times x times x times x 100 times. You can say, let's compute x squared, x to the 4th, x to the 8th, and so on. And you can just keep squaring it up. And you only have to do about log to the base. If you're taking it to power n, you only have to do about log to the base log to the base n of those repeated squarings to get the thing to to the power n. Okay, so Iggy is commenting that we met. Since I don't know who Iggy is from the handle, that makes it very difficult. But we met at the APL conference in 1989 in New York City. I remember it well. It was a time when I met, I think it's the only time I met Ken Iverson, creator of APL, in person. APL was a great language that had a lot of great ideas about list manipulation and so on, and had it was a sort of cautionary tale for language designers because it had great ideas. It was a great sort of list-oriented, sort of functional programming type language, and it had a number of very ardent adherents, but it was not widely used. And one of the problems was that the notation, it's sort of actually Ken Iverson's idea, and I'm going off on a tangent here, but Ken Iverson's idea was to sort of do for computation for algorithms what mathematical notation did for mathematics, of finding sort of a standardized way to represent algorithmic operations. Unfortunately, it didn't work out with APL because people just couldn't really understand the boatload of weird operators that sort of got presented as ways to do only certain kinds of algorithmic operations, ones with lists and so on. But there were lots of nice things. I mean, there was, whether it was grade up, grade down, which are, sort and sort by, all these kinds of things, or things like our range function was iota in APL. Actually, to show one piece of I kind of can show one little piece of trivia just for fun. Let's see if I can pull it up quickly. If I go to the hold on, I think I might be able to find it. Let's see whether I can find this. I am looking for the version 1 Mathematica book, the online version of that, full text legacy versions. Here we go. Version 1, here we go. And now, look at this, correspondences with other languages. And so there is APL. And so this is showing the correspondence between Wolfram language functions. Sorry, it's a bit old-fashioned typesetting here, but that's what you get when the typesetting comes from 1988. But this is the operators of APL compared to related functions in Wolfram language, and that's kind of interesting, actually. Encode and decode. Yeah, we now have better functions for this, actually, and we now have sort by for that. But otherwise, these are mostly the same. Anyway, okay. Well, fascinating coincidence here. Okay. Okay, well, we're getting off onto other topics, and I think this is turning into a general AMA, which I think is probably not the order of the evening. But there's a question of how did I choose the delimiters for Wolfram language? They actually came from my earlier system, SMP, where I chose square brackets to represent functions because I wanted to really have parentheses do their sort of their standard mathematical grouping operation. And I figured that it was clearer to have square brackets. And you could do all kinds of nice things, like, for instance, being able to actually have things like a paren x plus 1 mean a times 1 plus x, rather than having that be a function. And that was why I wanted to use parentheses to very clearly designate grouping, and square brackets to designate functions. All right, I think we should wrap up for the evening. I thank you all very much. Lots of fun stuff here. And go figure out why Rule 30 does what it does. Go solve these problems. This is I want to spend my $30,000. This is a great use of $30,000. I'm enthusiastic to. I have to tell you, when Alex Smith kind of won our Turing Machine prize, I was it was the happiest, one of the happiest uses, perhaps the single happiest use of $25,000 I've ever had. So let's repeat that in $10,000 increments for the Rule 30 prizes. Okay, well, thank you all for your participation, and well, don't know where in the world you are, but it's good night from me at least. Thanks a lot. Bye-bye.